All right. Welcome, everyone. Today's presentation, discussion, goat or car, the Monty Hall problem. So what's the big deal? Introduction, Let's Make a Deal was a popular game show in the 1970s, hosted by a fellow named Monty Hall, hence the name for the demonstration here. On this show, he had a segment called The Big Deal, and that involved picking from 3 doors to win a prize. This seemingly innocuous game is an interesting brain teaser and has caused arguments for decades. So what is the game? How does it work? So you're presented with 3 doors. 2 doors have a goat. 1 door has a prize. And in this case, the goat means you lose. Some folks might prefer the goat, but for the rules of this game, it means you didn't do well. So you have to pick a door. And after you pick the door, the host removes one of the doors that has a goat. And so now you're left with 2 doors. And you're now given the option to stay or change. And that's the basis really of what we'll be talking about. But before we get into that question, you might be asking, what is the prize? Well, what we have here is a 2010 Lada VAZ 2105S manufactured in Russia from 1980 through 2010, 30 years without design change. The Lada has a 4-speed transmission, 1.3-liter engine producing 64 horsepower, and a retail price of 300,000 Russian rubles. Getting up to highway speeds will be a challenge, but at least you'll be doing it in style. So that's the prize for this game today. Okay, so here's the crux of it. The chance of winning on your first pick is 1 out of 3, right? Pretty straightforward and obvious. 33%. The question really here is, will changing doors change your probability of winning? And if so, how much? And then what would you do? Would you decide to stay or change? I've prepared a group survey, and I will send the link in the Zoom chat. We can all watch the results come in live. So we can get a baseline on what folks feel. For the survey, there's no change. There's 1 out of 2, 2 out of 3, 3 out of 3, a bunch of different choices there. Results are coming in. 7 responses so far. Not sure how many folks we have on the call. 11, 13. Okay, 14. Got some math herding coming in. What if you picked the goat? That was a custom, so I left a custom answer section. So that's fun. 16 responses, okay. Okay, so looks like most of the folks said 2/3. So by changing your answer, your door, you feel like the impact would be 66%. So 43% of the folks chose that one. In second place here is folks feel it's if you change, you get 1 out of 2, 50% chance of winning. And then it's sort of varied and mixed across the rest of the options there. And 63% of folks said that they would change if given the option, and about 40% would stay. Okay. Interesting odds. So let's go back to the presentation. Surveys are in. So now that we got sort of the thoughts on what folks would do and how they feel that the percentages or the probability would be affected by changing, let's play a few rounds. I found this little, somebody made this game already on this website here. I started the programming in Python and recognizing the fact that I was doing this at the last second, realized that was a terrible idea. So luckily somebody did the work for me. So we'll play a few rounds here, not to make a proof, but just to get a feel for it and kind of see what happens. So I'll pick stay for the first few, and then we'll switch over we'll change to the switching doors. So let's pick one here, pick the first one. So I'll got the goat on door number 3. So I'll stay, as I was saying. So I lost. Okay, let's play again. Pick the second door this time. Like I said, I'm going to stay. Okay, this time I won. Play again. Pick the first door again. And the second one has the goat. I'm going to stay again. Okay, so we had 3 stays, 33% won. So that's kind of right in line with what we'd expect. Got lucky, I suppose, that it was so perfect. So now let's do some changes. So play again. Let's pick door 3. And we will switch now. Okay, we won. Let's pick door 2. Like I said, we'll keep switching on these ones. This time I lost. Play one more time. Let's pick door 1. I'm going to switch. Okay, so it just so happens that playing three of each, we got 33% for stay and 67% for switch. You know, doing 3 samples of each, it's not really that convincing, right? But that's what we got. And now you guys can see how the game works a little bit more clearly. Okay. So this is where the confusion enters, partly. So part of it is, you know, how do you ask the question? Like, what is the right question to ask to really think about this the right way? Here we go. If we look only at the third door, just the third door, what's the probability that it has a car behind it? Anyone can chime in if they want to on their thoughts. If you're just looking at that door, right, you might say it's 1 out of 2. You know it has a car or a goat, therefore it's 50%. What if you asked, what's the probability that out of the 3 doors, the third door is a winner, right? So if you phrase it that way. Yeah, people are commenting in the chat there. Sorry, I didn't notice the chat. So if you ask it that way, right, it's a little bit different. It's sort of the context of how you ask it. So in that case, obviously it's 1 out of 3, just based on how the question's asked. And then what if my question was a lot more verbose? So out of 3 doors, after picking 1 door, what's the probability of picking a winning door by switching after 1 losing door has been removed? That's really the question, right? You have to kind of factor in all of the variables there. So let's kind of put that to the side for a second. Let's look at it. Let's look at it a little bit differently. Let's say that we always stay. So we're never going to change. We're going to pick the first door. We're going to stick with it. What's our chance to win? We would say 1 out of 3, right? There's 3 doors. Pick the first one. 33% chance of winning makes sense. What's the chance of losing? So there's 2 doors left. So 2 out of 3, 66%. Pretty straightforward, right? Now, what's the probability of the car being behind door 2 or 3? Right, so not the first one, but factoring in both door 2 or 3. 25%, somebody said. So I should let you guys chat here, and I can read the chats off to the group here. Apologize, I'll be a little more patient here. 66%, right? So if door 2 can have a car or a goat, and door 3 can have a car or a goat, then it's 2 out of 3, right? What's the probability of the second door having a car after knowing that the second door is a goat? Anyone want to answer that in the chat? 0. All right. 0 out of 3. That's right. So when you kind of put those questions next to each other, they might get your brain kind of working there and kind of thinking through like, oh, there's some kind of correlation maybe, but I'm not sure what it means, but I feel something. So question is, if I switch instead of staying, does my losing probability of 2 out of 3 now become my winning probability? And that's more rhetorical, but if you want to comment in the chat, you can. I'll read it out. Okay, let's move on. Let's kind of carry some of those thoughts forward, right? Let's expand the problem. Now we have 100 doors. We pick the first door. The host removes 98 of the goats. That's, well, you see it here in the middle. What is the probability of winning if we stay? Anyone want to throw that in the chat? It's pretty self-explanatory, I suppose. It's 1 out of 100, 1%. And this is, again, where we're going to potentially argue or just not agree. What is the probability of winning if we change? Anyone want to throw any comments in there? 99%, somebody said, Jacob. 100 minus 1, 50 from farmer. Okay. And then again, I ask you, just should we stay or change? What are opinions in the chat? Stay or change? Stay. Gotta change. Change. So some stay, some changes. Not everyone's convinced still. Keep the goat. Yeah, that's probably the better answer. So let's look at this. Another way again. So let's look at it from a decision tree perspective. And so what this means is, what I have on the left here is a decision tree. And so this isn't the same thing exactly as having 3 different doors. It's more like, for each door, what are my choices? So like kind of simultaneously. It's not pick one, it's you get to pick all of them. So on the left, you have the decision tree. So choose the door, pick a door with a goat, you pick the door with a goat, you pick the door with a car, right? It's not that you are intentionally picking one or the other, it's those are all the possibilities. And on the right side is kind of a representation of playing the game along with the decision tree and how it unfolds. So one door with a goat has been removed. So you see the second step there. It goes from 2 goats being an option to 1 goat, right? Because 1 gets removed. Got a boot. Don't worry, the goat's fine. He's happy and healthy. So it was a soft boot. So now we have the 1 goat. We have the 1 car. Kind of makes you think 50-50 chance. But let's move on. So now let's say we're going to stay. So let's run down the first column. We picked a door with a goat. We're going to stay. We lost. Let's go down the second option. Pick the door with a goat. We stay. We lost. Third option, we happened to pick a door with a car. We stayed. We won. Makes sense, right? And on the right side, you'll see there's like this. This is kind of collapsed from 2 decisions, 2 options, right, to the same decision in one area right here. And then let's look at the changes. So we picked the door with a goat. We changed. We won. We picked the door with a goat. We changed. We won. We picked the door with a car, and we lost. And so this is literally all of the possible options, right, that the game has. This is all of the permutations of what could happen. And so if you look at it this way, it becomes a little bit more obvious kind of how the math is working, even though we haven't looked at the math yet. But you don't really need to, right? As long as you break out this decision tree. So you can see that the stay wins are 1 out of 3, 33%, and the change wins are 2 out of 3, 66%. Any questions or thoughts on that? Makes sense.
I want it to make sense so bad, but it still doesn't.
Okay. Did anyone want me to walk through it again? Or should we just move on?
Maybe at the end. I have questions, but I'll wait till the end to ask them.
Okay. All right, so now if you're just still not convinced, we can go the math approach. So I just asked the same question again from earlier. So out of 3 doors, after picking 1 door, what's the probability of picking a winning door by switching after 1 losing door has been removed? Right, and the question has to be that long because of all the variables and permutations. And so to approach that mathematically, there's what's called Bayes' theorem. In probability theory and statistics, Bayes' theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. So in other words, factoring in all of the options that you can choose, right? And then solving that mathematically. If you apply that to the Monty Hall problem, basically a lot of variables in math. I'm not going to walk through that because that's not the point of this presentation. But basically what we just saw in that logic tree is being done mathematically, and you again get to this 2 out of 3 option. If you want to dive into that further, I can point you guys, just ask me and I can point you guys to the math, more details on that. All right, so let's look at it from another perspective. Psychological confusion from biases, right? It's just more things that cause confusion. So there's a few different biases at work here, which Chris recently did a presentation on biases, which was fantastic, which actually gave me the idea to do this presentation. So the first bias here, the cover, is endowment effect. Emotional bias that causes individuals to value an owned object higher, often irrationally, than its actual value. So in other words, you pick that door, you feel like you own that door, like that's your choice. And so you just kind of innately, emotionally feel like it's better than the other door. You don't want to let that go. Second one is status quo bias. So it's another emotional bias, a preference for the current situation. The current baseline or status quo is taken as a reference point, and any change from that baseline is perceived as a loss. So in other words, you pick that first door, and just because you picked it, that's like your baseline, and changing from that feels painful. It feels like you're going to give up something, like you're losing something. And then the last one here, errors of omission versus errors of commission effect. So all other things being equal, people prefer to make errors through an action as opposed to action. So it feels less painful if you stay on the first door and let that be wrong than if you give up the first door and take the second one, if you make an action. So those are all things that factor into the psychological approach, or the psychological things that's happening while you're dealing with this game. What are the biases? Anybody want to throw any other biases out there that you know of that might affect this?
I can see all 3 of these at play with myself with this problem.
Cool.
I think there should be another bias called the coin toss bias, because it looks like a coin toss problem, but it's not.
Oh, interesting. Sort of a deceptive. Yeah. Okay. All right. Let's move on. So let's check in. So you're either not convinced still, you're convinced, or 1.b, you're not convinced but agreeing anyway. So let's take the survey again. So I have a separate survey link. We have stay, change, and this again. Let's see if anything. Let's see if folks got swayed or not. So I sent that in the chat. So 43.8% was the winning one before for changing. So let's see how that has changed. Okay. So far 11 responses have come in, and we've gone up a good 20% over the first survey to make a change when presented with the option. So we've convinced some folks, but there's still one person that says stay and one person that says this again. Thank you, Benton, for doing that. I'm sure that was you.
No, it actually wasn't me.
Oh, was it you? Okay. All right, so there's one person that says stay. All right, so we really got to do something here to convince that one person. And this is, whoever that was, this is for you. So we discussed the logic, we discussed the biases, we discussed the math. You're still undecided. Let's do a brute force approach. So last night I stayed up putting together this little model in Excel to really drive this point home and do a brute force approach. So I have this laid out. There's a table here where the simulation happens. You have rounds, you have your 3 doors, car, goat, goat. You have a winning door that's chosen at random between 1 and 3. So every time the simulations ran, it chooses between 1 and 3, 1, 2, or 3. And then like in our examples, we were always picking the first door, right? Which may not feel very sincere or fair. So I'm having the simulation choose a door as well. So there's a winning door that gets picked randomly, and there's a first door that you choose that gets picked randomly. And then we'll calculate, we'll track both staying and changing for every single round of simulation. And I have some data here that can, kind of help us follow along with what's happening. So the total rounds that we run will get tallied here. This table will keep track of summarizing the performance of staying or changing. So we can see the wins counted, the losses counted for each, and then a total in case you think I'm cheating somehow. You'll see that the totals add up and match the rounds. And then also in case you still don't trust me, which is completely understandable, I'm counting the number of times each of the doors wins so that you can see over time as we scale this up, there should be a fairly even distribution of doors that win, right? You would expect around 33%, 1 out of 3 for each door to kind of accumulate over time, right? So I've got all the things in place. So I can just run this calculation, right? So we do it one time. The change one, in this case, door 1 had the car. Run it again. Let's get a more different looking result. So first 2 have a goat. The third one has the third door has a car. The winning door is 3. The choice was 1, so they stayed, so they lost. So if they would have changed, they would have won. Let's run it again.
I have a question.
Yep.
In this simulation, well, never mind. You just proved it. So door 1 is not always a car.
That's
door
right.
2 is not always a goat. Okay.
Yeah, the winning door and the choice, your initial choice, are all changing. So it makes sense, right? So let's scale this up now. So let's do. A few more tests. So we're doing 15 rounds now, and this is all parallel. So like I can run this calculation, and it's going to run 15 rounds of the simulation, and you'll see like what's happening with these graphs, right? So what you're seeing here is it's doing 15 rounds, and then this is plotting how the win percentages look cumulatively for staying or changing. So there's 15 rounds. They're staying is winning, it's losing, it's winning, it's losing, it's winning, it's losing, etc. It's approaching 33%. So I had 5 wins for stay, 33%. And then the changes are the green line. Those are winning, losing, winning, losing. They had 10 wins overall, which is 67%. But let's run it again, right? So that it looks different every time, right? It's like, well, why is that? And that's just because the numbers are still too low, right? It's like the behavior is too erratic. So let's make this a little bit bigger. Let's do like 200 in parallel. So now that we have more rounds happening all simultaneously, it's pretty interesting, right? Like when you watch the line change, like these crazy zigzags, you'll have a run of like wins, right? For change, for example, or stay. Like sometimes it starts running, which is just we can dive into like gambler's fallacy kind of thing. But that can be a different presentation. But it's pretty interesting. You can see the behavior. It's fairly erratic. It goes up and down. But then after, in this case, around 80 or so, it starts to kind of settle out into like a mean. And then you'll see places where it like starts to go away from that, and it comes back and it goes away. And it'll do that. Like, you can run this a bunch of times, right? So this is just showing like kind of the chaos of like probability, and like especially at lower sample sets, right? You just get this craziness. Let's see if we can get one where the stay is like winning more. That'd be interesting. Can't really get that. Oh, there's one. So that's pretty interesting, right? So it reran all these 185 rounds, and there were quite a long run where stay was actually winning more of the time, but then even the stay has to fall towards what we expect mathematically, which is indeed that changing should win 66% of the time, right? Which is what we were showing in some of those examples. And maybe you're still not convinced. Let's do this even larger. Go to like 1,000. Just to really prove the point. I forgot how many columns there were. Hope I don't break it. Oh, I probably broke it. Let's see. Oh no. Yep, I broke it. Hell. There we go. So now we've run the simulation 1,051 times. We have 329 wins, 722 wins for stay, which is 31%, 722 wins for change, which is 69%. So still not exactly, mathematically what we were predicting, right? But this is like a real scenario where sometimes things will be a little bit off from what you should get probabilistically. However, you see that the line starts to get pretty darn smooth. It starts to get pretty straight as we get really far out here. And so we can run this again, right? 64% winning for change, 36 for stay. We run a bunch of times, and it's always going to be settling into about where we expect it to be. And you can literally do this. I mean, if you don't trust my simulations, get a deck of cards, draw a car on every third one, shuffle it up, play the game yourself. Play it 1,000 times and let me know how that goes. But you definitely will get the same result. Okay, so back to the presentation. Darn it, hold on. Why did I go to the beginning? Okay, so that's my brute force example. We're at the 33-minute mark here. So open the questions. That's the end of the presentation. Any questions, discussion?
Quite interesting, John.
No goats were hurt while making this.
Do you know if Monty Hall knew ahead of time what he had going on, or do you think he just did a 50-50, or he thought it was 50-50 too?
From what I've read, there was no indication that he was like a stats major and like understood like the complexity of the problem. But there might have been somebody, right? I mean, if you have this big network game show, you would think somebody's going to understand that there's a bias, but I don't know. It's hard to tell. Like I didn't find any conclusive information either way.
That he started out as a coin under the glass con artist, not even, the street con artist.
Cost of maintenance on 2010 Lada. It is amazing that car never didn't change for 30 years. So weird.
It was funny.
Okay, no questions, no arguing.
I have a
There'd be more
question.
arguing.
I have
Go
a
ahead.
question. Can you go back to the slide where you're showing the 100 doors?
Sure.
Okay, so what is the probability of winning if we stay? So is it not 50%? Because if the host removed 98 cards and you're only left with 2 other cards or doors, excuse me, doors.
Mhm. The thought is that the rest of the doors, the chance of winning by changing would be 99 out of 100. That's kind of what that's what the thought experiment is sort of alluding to. But that's why this is exciting, right? And interesting because it's all interpretation. You see it one way, another person sees it a different way. And this is just a tool to point that out and discuss it further. There's no right or wrong answer really when it
Well,
comes
there is.
to.
There is.
Well, yeah, there is.
There
In terms of interpreting some of these examples, you can interpret them many different ways, and that's sort of the point. But mathematically, yes, there is a solution, which we showed.
Is it, I mean, by making a change, you're getting 2 out of 100 choices, whereas if you stay, you're only making 1 out of 100 choices. And over time, 2 out of 100 is better. Is that basically it?
The thought is by changing, you have a supposedly the thought is you have a 99 out of 100 chance. But like depending on how you interpret it,
But I
don't
don't
know.
understand.
It's not so
how-
convincing, right?
So kind of the way that I see it is you're not choosing between 2 cards. You're choosing between the representation of winning and the representation of losing, which is like the odd, like, so your 2 options are not, card A and card B, because what makes this work the way that it does is the host has the knowledge of what 98 losers are. And so it's no longer like a 50, it's not a 50-50 shot like it kind of appears to be, because the host has removed those 98 losers. And so you're choosing between your odds on the first card and your odds on the second card, but the second card is going in with the base assumption that 98% of those losers are gone, as opposed to those losers being there when you pick the first card.
Yeah, I
Yes.
recognize that, like, the 98 cards are significant. But I don't, it's like not clicking.
I think this is one way to think about it too, is this slide is pretty key. It's like if you know your first choice is 1 out of 100 for the 100 door example, then you're by not changing, you're going to lose 99% of the time. So inversely, if you switch, you're going to win 99% of the time. Right.
Yeah, it makes sense on like that level. Yeah.
It's not intuitive. I mean, and that's why this problem is so fun. Okay. Does it cost more? Any other questions, thoughts?
Also prior knowledge that there are 2 losers and 1 winner. Right, there's only 1 winner.
Yep. 2 losers, 1
So-
winner.
So that's why switching, right? You switch, you win. 2 out of 3 times.
Yeah, and the eliminating the one goat is the whole, obviously the whole crux of this thing.
You share this deck so I can pour over it.
I think I was